Hi everyone. In this video, I want to work through the 5 questions from Classwork for this section. The first question has 3 parts. So these 3 equations I want to solve. 3 algebraic equations, and we're going to use what I referred to in class as the golden rule of algebra. And when you have an equation, which is a mathematical statement, you can do anything you want. You can make any change you want to one side as long as you make the same change to the other side. So for this first equation, we have 6x is equal to 78. What we want to do is isolate x, get x by itself. Anything that's affecting the x, we want to eliminate it. So right now, x is being multiplied by 6. So what we want to do is eliminate that times 6. The way we do that, the way we eliminate things that we want to get rid of in an equation, as we apply the opposite operation. So the opposite of times 6 would be divide by 6. And if we take the left-hand side of this equation, we divide it by 6. Oh, that's going to give us exactly what we want, x by itself. All right, the only reason we're allowed to divide the left-hand side by 6 is because we do the same thing to the right. So if we divide the left by 6, we have to divide the right by 6. So on the right, we have 78 divided by 6, and that should give us 13. And 13 is the solution. Let me circle that in green. 13 is the solution because if we replace the x with the number 13, we get a true statement. 6 times 13 is equal to 78, and that is true. So you could divide both sides by the same number. The second problem, x minus 9 is equal to 44. So we're going to take the same approach. We want to eliminate something. In this case, we want to eliminate a minus 9. And so the opposite of minus 9 is plus 9. We call this the inverse operation, but just think in terms of opposite. The opposite of minus 9 is a plus 9. So if you take a minus 9 and a positive 9 together, that gives you 0. They cancel each other out. And if we do something to one side of the equation, again, we have to do the same thing to the other side. So if we're adding 9 to the left, we have to add 9 to the right. On the left, we get x. That's what we're looking for. And on the right, 44 plus 9, that'll give us 53. And so that's our answer here. This is about as simple as it could get. Simple doesn't mean easy. Simple means short and concise. These are one-step problems. Doesn't get any shorter than one step. Now the next one over here, we got 14 is equal to negative 2/3 times x. So this is similar to the problem in part A, where we have x times a number. So we could divide both sides by 2/3. We could divide both sides and say, okay, or by negative 2/3 and say, okay, we'll divide the left by negative 2/3, and we'll divide the right by negative 2/3. I'm going to take a slightly different approach here, though. Instead of working with a fraction, I'm only going to work with the whole numbers. So I'm going to look at the numerator, the 2, separately from the denominator. Remember, fraction means division. So I'm just looking at that over 3, that 3 on the bottom. That means dividing by 3. So the opposite of dividing by 3, let me rewrite this a little bit bigger. 14 is equal to negative 2 over 3 times x. So what we could do is we could multiply by 3. We can multiply by 3. So if we times by 3 and we're dividing by 3, those two cancel each other out. We're not working with the whole fraction, just the bottom, just the dividing by 3. So on the right-hand side, that will give us a negative 2. The negative 2 is still there, so negative 2 times x. So we're not working with the fraction, even though it's a fraction. We're working just with the denominator. And then separately, we'll deal with the -2. As always, whatever we do to one side of the equation, we have to do the same thing, make the same change to the other side. So I'll times the left by 3. And that'll give us 42. So I'm doing this in 2 steps. Now, we're not done yet because we don't have x equals. We have a -2 times x. So what we could do is the opposite. So now this looks very similar to part A. The opposite of times a -2 is divide by -2. We could divide both sides by -2. On the right, the times -2 and divide -2, they cancel each other out. -2 over -2 is equal to 1. So we basically have 1x, or just x. That's what we want. And on the left, also, we're dividing by -2. If we take 42 divided by -2, that will give us a negative, because a positive divided by a negative is negative. That'll give us -21. All right. So that's our answer for part C. Now, problem 2. Slightly more complicated. So we're starting with at the base level, one-step problems, and then working up from there. So in this second problem, we've got 5 times x plus 3 is equal to -17. All right, so we got 2 things to eliminate. We got to get rid of that times 5. We want x by itself, right? So we want to get rid of the times 5. We also want to get rid of the plus 3. We got 2 things to do. So to eliminate a plus 3, we would subtract 3. To eliminate a times 5, we would divide by 5. Now, you could do it in any order. Right? We could deal with the 5 first or the 3 first, but one path is going to be a little bit easier than the other. When I say easier, I'm thinking in terms of fractions. You don't want to bring fractions into a problem that doesn't have fractions. Right? So if we started off by dividing by 5, remember, you can't just divide part of one side. You can't do this. Right? This is a mistake. The rule is whatever you do to one side, you have to do to the other side. So if we're dividing by 5, we would have to divide the entire left side by 5, which means the 5 in front of the x would cancel, but then we would have the fraction 3/5. So we don't want to do that. We don't want to bring fractions into the problem. So I'm going to deal with the plus 3 first. So we could subtract 3 from the left-hand side. So the plus 3 and the minus 3 cancel, leaving us with just 5x. So we're getting closer to what we want. So now we have 5x is equal to, and on the right-hand side, we have to do the same thing, minus a 3. So we've got -17 minus 3. That'll give us -20. And now we have one thing left to do, one more step. We have 5 times x. We want x by itself. So eliminate the times 5 by dividing by 5. Notice I'm given a nice horizontal line to separate my steps. It's not required, but it helps me just visually keep my work nice and neat and organized. Whatever we do to the left, we have to do to the right. So on the left, the times 5, the divide by 5, they cancel. And we're left with x is equal to -20 divided by +5 will give us -4. All right, so -4 is our answer to this one. Moving on, number 3. Slightly more complicated, right? Just in terms of number of steps. So we've got 2 times x minus 1 divided by 5 is equal to 9. All right, so we've got a 2, we got to deal with that. We've got a -1, we got to deal with that. We've got a 5, we got to deal with that. So this will be 3 steps. I like to eliminate fractions first. So to eliminate the over 5, the divide by 5, remember fraction is division. So this is dividing by 5 in the original problem. So I'm going to do the opposite. I'm going to times by 5. Doing the same thing to both sides. So on the left, the times 5 and the divide by 5, they cancel. So we're left with 2x minus 1. And on the right, we got 9 times 5 is 45. All right, so we just keep going. Eliminate the things that are around the variable. We want to get x by itself, so we want to strip away everything that's affecting the x. Right now, at this point, x is being multiplied by 2 and then subtracted by 1. So we'll deal with the -1. Same as the previous problem, or back in problem 1. Opposite of -1 is +1. So if we add 1 to the left, the -1 and the +1 cancel. Now we're down to 2x. Whatever do to the left, we have to do to the right. So I'll throw a +1 over there on the right. All right, so we've got 2x on the left is equal to 46. We're getting close, incrementally, slowly getting closer and closer to what we want. X is equal to a number. All right, last thing to do, x is now being multiplied by 2, so I'll divide by 2. Same thing to the other side. So the times 2, divide by 2, they cancel. So we're left with x on the left. 46 divided by 2 should give us 23. All right, so x equals 23. That's our final answer. The next 2 problems are word problems, and we're not solving them. So this next problem, you're part of a team that is designing a raised garden that will be on campus. One of the details of the garden is that it is in the shape of a rectangle that is 4 times as long as it is wide. If we let W represent the width of the garden, give an algebraic expression that represents the length. Right, give an algebraic expression, no equation, there's no equal sign here. It's just an expression for length. Later in the semester, we'll actually solve a problem like this, but this is just basically step 1, the setup. Now, I've said this before, I'm a very visual learner, so as soon as I feel like I could draw a picture to represent the word problem, that's what I do. So I'm looking at this. The garden is in, oh, no, I don't want that thick line. Pen. The garden is in the shape of a rectangle. So, boom, I'm drawing a rectangle. So there's my garden, represented visually. That is 4 times as long as it is wide. Ooh. If we let W represent the width of the garden, right? So remember, algebra, we're using symbols to represent unknown numbers. We don't know what the width is. We know it's a number. We just don't know what the width actually is. So we'll give it a symbol. We'll call it W. Usually the short side we call the width, but it doesn't matter. Just one of the 2 sides we'll call width. So if we let W represent the width of the garden, give an algebraic expression that represents the length. The algebraic expression could be a single variable, a single letter. But we could say L, but we don't want to do that, L for length, X or whatever. We don't want to use a second variable. We want to, as soon as we establish one symbol, we want to stick with just that one symbol. So I'm not going to use L for length. I'm going to use what's given in the problem. One of the details of the garden is it is in the shape of a rectangle. That is 4 times. Oop, I wanted to use a highlighter there. Is 4 times as long as it is wide. Right? The length is 4 times the width. And so without saying those exact words in the problem, that's the meaning. That's what it means. The length of the rectangle is, sorry, I keep going to the next problem. The length is 4 times the width. So if the width is W and the length is 4 times the width, then our algebraic expression for length will be 4W. So for this problem, all we're doing is giving a symbol for length. So our symbol for width is W. Our symbol for length is 4W. Now, if we were solving the problem, we would use that in an equation. But again, this is just step 1 of the solving process. So we have 2 unknowns here. The length is W, or sorry, the width is W, and the length is 4W. In the next problem, we actually have 3 unknowns. All right, so on number 5, Marcos has been collecting coins for some time now to save for a gift that he's planning to buy for himself. All right, so he's saving coins, no pennies, only nickels, dimes, and quarters. All right, so that's important. We don't have 4 unknowns, we have 3. Only nickels, dimes, and quarters. He has 3 times as many nickels as dimes. He has 11 more quarters than dimes. Express the number of each coin with an algebraic expression using only one variable. So this problem is referring to or mentioning 3 unknowns. So we have number of nickels, we have number of dimes. You could shorten this to just nickels, dimes, and quarters. I'm just writing it out. Number of dimes and number of quarters. Each one needs a symbol, right? But we can only use one letter, one variable. We can't call them all X. One of them has to be X. We could either say number of nickels is X and then figure out the other 2. We could say number of dimes is X and figure out the other 2. We could say number of quarters is X and figure out the other 2. You got to pick one of them to be X. Well, let's go back to the problem. Oh. He has 3 times as many nickels as dimes. Right? So we have one statement. We have one statement that connects nickels and dimes. Right? He has 3 times as many nickels as dimes. Then we've got another statement and 11 more quarters than dimes. All right, so we have another statement that tells us how quarters and dimes are related. So it seems like if we know how many dimes there are, then we could use that to figure out how many nickels and quarters there are. So I think in this case, it makes the most sense to let X represent the number of dimes. And now we could figure out the other 2 based on the variable x. So if we look at the highlighted, the yellow highlighted statement, he has 3 times as many nickels as dimes. He has more nickels, actually 3 times as many as the dimes. So we could let our symbol that represents number of nickels be 3x. We don't want to use x, y, and z or n, q, and d. We don't want more than one variable. So if dimes is x, based on what we're given, nickels could be 3x. And then the statement that's highlighted in green, 11 more quarters than dimes. So there's also more quarters. How many more? Well, 11 more. 11 more means plus 4. Plus 11, sorry, plus 11. Right? 11 more than means addition. More than means addition. So we could say x plus 11 is our symbol that represents the unknown number of quarters. So we have x dimes, we have 3x nickels, and we have x plus 11 quarters. Again, this is where we stop. So this is our answer. This is our answer right here. We've just expressed these unknown quantities using mathematical symbols, a 3x, an x, and an x plus 11. Later, again, we'll solve problems like this. This will be step 1 in the solving process. This is how the problem starts. Take everything that's presented to you that's unknown and give it a symbol. Now, when I say symbol, that could be a single letter like x, or it could be something more complicated like 3x or x plus 11. But each of the 3 are now represented symbolically. All right, that does it for these 5 problems of classwork.